problem which we want to solve is integral 0 to a upon root 2. Integral, it is 0 to under root a square minus y square. It is log of x square plus y square dx dy. The same statements we are required to make here, that is, the limits are in y, therefore these are values of x. So on strip x varies from x equal to 0 to x equal to under root a square minus y square. The strips are parallel to x axis. Parallel to x axis, and such strips are taken from y equal to 0 to y equal to a upon root 2. Obviously the four curves that we have are respectively x equal to 0, then x square equal to a square minus y square, which implies x square plus y square equal to a square, y equal to 0 and y equal to a upon root 2. We can now draw the figure corresponding to the particular area of integration. One of the major curve over here is again a circle, x square plus y square equal to a square. That is a circle having center as origin and radius a. So we can draw that circle. This is a circle, x square plus y square equal to a square. So far as x equal to 0 line is concerned, it is y axis. So far x equal to 0 is concerned, it is y axis, and y equal to 0 line is x axis. So the three of the four curves are already drawn, and now we are required to draw the straight line y equal to a upon root 2. Y equal to a upon root 2 will be a straight line which is parallel to x axis, and then we will have to check what is the corresponding x value, because whenever you draw some line parallel to x axis, it is going to cut circle at some point. So we will have to locate the corresponding point on the circle, and for that we are going to substitute this value of y in the equation of circle, which gives us x square plus a square by 2 equal to a square, that is x square equal to a square minus a square by 2, which is again a square by 2, and so x comes out to be plus or minus a upon root 2. So there will be 2 points of intersection. One is a upon root 2 x coordinate and y coordinate is a upon root 2, and the other intersection point will be minus a upon root 2 and a upon root 2. So as we get two different points of intersection and the line is parallel to x axis, we will have to consider these 2 points, and you can observe that one point says that x coordinate is equal to y coordinate. That means it is going to be the point on the line x equal to y. And so we can approximately consider a 45 degrees line, and this will be the point a upon root 2, a upon root 2. So he is talking about the area such that the strip starts on x equal to 0 and goes up to the circle, and such strips are taken from y equal to 0 to y equal to a upon root 2. This will be the area of integration. Let us consider the next problem in the series. We are required to change the order of integration, and the problem says it is integral 0 to a upon root 2, integral 0 to under root a square minus y square log of x square plus y square dx dy. We will have to observe the limits and check the variable which is present in the limit. It is y. So we can say that limits are in y. Therefore, these are values of x. Therefore, strips are parallel to x-axis. Therefore, the strips are taken parallel to x-axis. So, on strip, x varies from x equal to 0 to x equal to under root a square minus y square, and such strips are taken from y equal to 0 to y equal to a upon root 2. So we are now required to draw the region of integration. The region of integration will comprise of 4 curves: x equal to 0, x equal to under root of a square minus y square, which can be interpreted as x square equal to a square minus y square, that is nothing but x square plus y square equal to a square, which is a circle with center origin radius a. Then the curve y equal to 0, that is a straight line x-axis, and a curve y equal to a upon root 2, which is again a straight line parallel to x-axis. So there are 4 boundaries to this particular region. Let us draw that circle first. This will be circle x square plus y square equal to a square. X-axis, that is y equal to 0, this is one of the boundary. Y-axis, that is x equal to 0, is also a boundary. This is circle x square plus y square equal to a square. And the point or the line which is y equal to a upon root 2 has to be drawn somewhere here. It is going to be definitely below 0a point, because a upon root 2 value is greater than 1. This particular line is going to cut circle at some points, and so to find out those points of intersection, let us substitute y equal to a upon root 2 in the equation of circle, so that we will be getting points of intersection. It will be x square plus a square by 2 equal to a square, x square equal to a square by 2, x equal to plus or minus a upon root 2. So the 2 points of intersection will be a upon root 2, a upon root 2, and the second one is minus a upon root 2 and a upon root 2. Observe that as x is equal to y in this case, it must be lying on the straight line y equal to x somewhere here. It's exactly the point which is on the line x equal to y, and we are talking about a straight line parallel to x-axis in this case, whose equation is y equal to a upon root 2. So we have drawn the 4 curves, first one being x equal to 0, that is y-axis. Second curve is the circle, third curve is y equal to 0, and the fourth is this particular line. It is the region bounded by these 4. This should be the region. We will just confirm it from the strips. The strip begins on y-axis and goes up to the circle. The strip is parallel to x-axis, and such strips are taken from y equal to 0 to y equal to a upon root 2. This is the region of integration. Our aim is to change the order of integration, and then proceed further. To change the order of integration, this particular strip now should be taken parallel to y-axis. If we take strip parallel to y-axis, then we find that on strip y varies from y equal to 0 to y equal to a upon root 2, but is not a universal thing. In this particular region, the strip will start on x-axis but will go up to the circle. That means the region will get splitted up into two different areas. One of them is going to be a rectangular, to be precise a square area, and the other one is going to be the area which is not even the sector of a circle, it is a portion of that circular area. For this we will go for some enlarged figure which will appear like this. There is a portion of a curve, circle, and the region under consideration is like this. This was that region. This line has got equation x equal to a upon root 2 because this particular point is a upon root 2 comma a upon root 2. We are also aware of the fact that this point is a comma 0. This was origin. This was y-axis. The remaining portion of the circle is not shown. This was the region of integration. Now the strip is to be taken parallel to y-axis. I will call this as area 1 and this as area 2. The strips are taken parallel to y-axis. Therefore, the given integral can now be written as, I will be talking about area 1 and area 2. So on area 1, on strip y varies from y equal to 0 to y equal to a upon root 2, whereas over here y will vary from y equal to 0 to y equal to under root a square minus x square. I have found out this particular value from equation of circle, and such strips are taken from x equal to 0 to x equal to a upon root 2. So such strips from x equal to 0 to x equal to a upon root 2 on area 1, whereas on area 2 it will be from x equal to a upon root 2 to x equal to a. And now we can write the integrals, and it will be written as integral inner limits from y equal to 0 to a upon root 2 and x equal to 0 to a upon root 2. This is area 1. Function remaining the same, log of x square plus y square dx dy, plus double integral on that area 2 where y varies from y equal to 0 to under root a square minus x square and x equal to a upon root 2 to x equal to a, log of x square plus y square dx dy. This is going to be the required answer after changing the order of integration, that is, the strips which were taken parallel to x-axis initially are now parallel to y-axis. Evaluation, of course, in this case could be slightly problematic because the logarithmic term is involved, and secondly the function is of the second order, and so probably we will have to do it by some other method called as taking the strips in the radial form, which we will be doing afterwards in the due course. Here we are concentrating only on the change the order of integration. After discussing this change of order of integration problems, let us now proceed further with the evaluation of double integration type of problems, where it will not be explicitly mentioned as whether we are required to change the order of integration, or if possible can we integrate it directly. Also, these are the problems where we are not going to specify, or the problem doesn't make a mention about what is the region of integration. Instead of that, the limits of integration are directly given to us. From those limits only we are required to analyze as how the strips are taken, whether they are taken parallel to x-axis or they are taken parallel to y-axis, and then accordingly we will have to deduce as with respect to which variable we are required to integrate the particular integral. And if we find that, for example, if the limits are in y, then we will be saying that these are values of x, and we should be taking the integration with respect to x first, because the strips are parallel to x-axis. And if the function in x is critical, that means it cannot be integrated with respect to x at the initial point, whereas the functional part which contains y is integrable. In that case, we will prefer to integrate it with respect to y first, which is with the limits, with the given limits, may not be possible. Because the limits are in y, these are values of x, therefore the user has taken strips parallel to x-axis, and as the strips are parallel to x-axis, we should be integrating with respect to x first. If we want to integrate with respect to y first, because the function is non-integrable with respect to x at the initial point, then we will have to change the order of integration, take strips parallel to y-axis, rewrite the given integral. For that you will have to again go for finding the region of integration, changing the order or the manner in which we have taken the strips, rewrite the integral, integrate it with respect to y, and then probably you will be getting some portion in terms of x, so that along with the original function which contains non-integrable part of x, now the overall thing could be integrable. And so the problem may contain something called as the change of order in itself, which is not mentioned within the problem statement. This is one type of problem. The second type of problem is one where the limits are constant. That means it is given that all the four limits, that is the outer limits as well as inner limits, they do not contain any variable. Of course, up till now we have seen so many double integrals, and we know that the outer limits cannot contain any variable as such. Outer limits must be necessarily constant, whereas the inner limits could be in terms of y or in terms of x. Now the question is, what will happen if the inner limits are also constant? Outer limits are always constant. So if all the four limit values are constant, then in that case the region happens to be the rectangular region. And if the region is rectangular, changing the order of integration is simply switching the positions of these two integrals. The particular problem can be solved without actually going for the region of integration. But of course, there will be always a decision as which limits correspond to which variable. If it is simply written as integral a to b, integral c to d, some function of xy dx dy, then it is not possible to make out where a and b are values of x or values of y. And so for that reason, for that particular reason, probably the problem statement might be splitted in terms of dx and dy written separately. Let us have a look at the next exercise that we have. The very first problem that is given to us is integral 0 to 1, integral 4y to 4 e raised to x square dx dy. Now here the limits are not constant, the inner limits are in terms of y, and that means these are values of x, and the user has taken strips parallel to x-axis. So the limits are from x equal to 4y to x equal to 4 and y equal to 0 to y equal to 1, and we are required to integrate with respect to x first, but we have a function as e raised to x square, which is non-integrable, because e raised to x square you don't have any direct formula. Instead of that, if it would have been the y value which is to be integrated, probably my job would have been simpler. And so this problem will lead to change the order of integration. In the second problem, the limits are 0 to infinity, outer limits, 0 to 1, inner limits, and observe the manner in which the problem is stated. It is 0 to infinity dx, which indicates that these are values of x, and 0 to 1 dy, that means these are values of y. Initially in earlier problems I have said that whether you write it as dx dy or dy dx doesn't make any difference, because it is the product that you are going to mention. But in this case it really matters as whether you are going to write dx over here or dx over here, because accordingly the limits are going to take the particular values as values of x or values of y. So here x equal to 0 to x equal to infinity and y equal to 0 to y equal to 1, we are required to integrate with respect to y, obviously, and probably we may integrate it or we may not. That is to be considered afterwards. Problem number 3, again limits are constant. We are required to integrate with respect to y first, which is going to be a bit difficult task, because there is a term e raised to minus y, y raised to x and log y. Product of 3 terms to be integrated could be a tough task. Rather than that, if it would have been simply y raised to x, then it is the formula which is to be applied for integration with respect to x is integration of a raised to x, which will be a raised to x upon log a, and the job can be done easily. Probably in this case it will be y raised to x integrated with respect to x will result in y raised to x upon log y, and that particular integral will result in 1 upon log y, which is likely to get cancelled over here. And so you can integrate it. That could be our first impression. So this problem will again lead to change the order of integration, but as I have mentioned it earlier, as the limits are constant, changing the order of integration is simply switching these two limits. The outer limit integral should be taken as inner integral should be shifted to outer one. This will become something into dy and that function into dx, and we can proceed with the integration. Whereas if you have the look at the remaining two problems, then in both of them the inner limits are in terms of x, so these are values of y, and so he wants to integrate with respect to y first. Probably both the integrals are such that y is integrable, and so we can straight away proceed with the solution without actually going for change the order of integration. So the 3 types of problems which I was mentioning in the earlier case at the beginning of this particular lecture, all the 3 types are over here, where the function may not be integrable. You will have to change the order of integration and proceed with the integration. There are 2 such examples over here. There are 2 examples where all the 4 limits are constant, and so if required we can change the order of integration very easily. Those are the 2 types of problems, and remaining 2 problems are such that even if we don't change the order of integration, as it is, we can integrate them. Let us proceed with the solution of these problems one by one. Let us now start solving from the first problem. This being our 3rd lecture or so, it is not necessary that I will be going through each and every step. Probably we can solve it in a faster manner. Of course, in the exam you are required to write down all these steps, like limits are in y, so these are values of x. On strip x varies from x equal to 4y to x equal to 4, and such strips from y equal to 0 to y equal to 1. I get the 4 bounding curves. X equal to 4y will be the line where when I substitute y equal to 1, x will come out to be 4. So I will have to locate that particular point 4, 1, which is over here, and the straight line passes through origin because it is in the form y equal to mx. So this is a straight line x equal to 4y. X equal to 4 is a straight line like this. Y equal to 0 is a straight line which is x-axis, and y equal to 1 is a straight line like this, because we have already got it as 4, 1 as the point through which we are passing it. Now once we draw all these 4 curves, that is x equal to 4y, x equal to 4, y equal to 0 and y equal to 1, we know that the strips are taken parallel to x-axis, and on strip x varies from x equal to 4y. That means he is going to begin the strip on this particular line, and it is being the lower limit. This is the left value that we have. From here the strip will start and will move towards right. That means the strip starting point is x equal to 4y, will go up to x equal to 4. This is how the strip is taken, and such strips are taken from y equal to 0 to y equal to 1. The region of integration in this case will be the lower triangle. Why were we finding the region of integration? Because the function to be integrated was e raised to x square, which cannot be integrated with respect to x first. So we will now take strip parallel to y-axis. If we take strip parallel to y-axis, the given integral can now be written as, on strip y varies from y equal to 0 to y on this particular straight line, which is going to be y equal to x upon 4, and such strips are taken from x equal to 0 to x equal to 4. Leftmost strip is at origin, rightmost is at x equal to 4. It is e raised to x square dx dy. We will have to integrate with respect to y first, so it will be x equal to 0 to 4. E raised to x square is constant. Integration of dy is y within limits y equal to 0 to x upon 4 dx. One of the simplest type of integral that we have here. So it will be integral 0 to 4 e raised to x square as it is. At upper limit it is x by 4, at lower limit it is 0 dx. Ultimately 1 by 4 can be taken outside. Integral 0 to 4 e raised to x square into x dx. Using the formula as integral e raised to fx into f dash x dx, with the substitution in mind as fx is equal to t, therefore f dash x dx is dt. I repeat, e raised to fx into f dash x dx, with the substitution as fx equal to t, we will have f dash x dx as dt, and so this integral will turn out to be e raised to t, and f dash x dx is dt, e raised to t into dt, it will be the integral value as e raised to t, and you can resubstitute t as fx, it will be e raised to fx. If I am to use this particular formula, in this case I have e raised to x square, and so f dash x will be 2x. Out of that x I already have. So we will be simply adjusting 2 over here, and will directly use the result. So it will be 1 upon 8 e raised to x square into 2x dx will be integrated as e raised to x square only between 0 to 4. And so it will be 1 by 8 into bracket e raised to 16 minus e raised to 0. Final answer comes out to be e raised to 16 minus 1 upon 8. Thumb. The first problem has resulted in the answer as e raised to 16 minus 1 upon 8. In the second case, limits are constant. Outer integral indicates that these are limits of x, inner integral are limits of y. So it can be written as integral x equal to 0 to x equal to infinity, integral y equal to 0 to y equal to 1 upon 1 plus yx square dx dy. dy dx, whatever. As inner limits are of y, user has given the steps parallel to y-axis and we are required to integrate with respect to y first. Question is whether we can integrate it with respect to y first. Here we are interested in 1 upon 1 plus yx square to be integrated, and this integral will come out to be, if you make the substitution as 1 plus yx square equal to t, then it will be 1 plus yx square equal to t. Then after differentiation it will be x square dy is equal to dt, and so you are required to adjust for x squares because dy will be dt upon x square, and so you can integrate it, and the integration in this case will come out to be 1 upon t into dt upon x square. This dt upon t will result in log t, and you already have 1 upon x square. When you substitute for that log t as 1 plus yx square, and when you substitute the limits of y, it will be from 0 to 1. If you substitute y equal to 0, fine, it is log 1 which is 0. If you substitute y equal to 1, it will be 1 plus x square, log of which will come into picture, which is to be integrated with respect to x with 1 upon x square that we have already introduced. Probably we find that the integration is possible. Let us continue with the solution. This will be always a good policy to check whether the function is integrable, because otherwise we will start solving it and we could have a feeling in between that we should have changed the order of integration and then it would have been easier. So I will now straightforward proceed with the integration with respect to y, and integration with respect to y in general also can be done because it is going to be log of 1 plus yx square, and you will have to always divide by the coefficient. Here I am using some other formula than the one which I have already shown you. The formula that I have used is something like 1 upon a plus by dy will be integrated as log of a plus by upon b. So using this particular result, I could get it very fast. Of course, substitution is another way. X square is constant for the time being, so it is x equal to 0 to infinity 1 upon x square as it is. At upper limit it will be log of 1 plus x square minus lower limit value it will be log of 1 plus 0. So it will be integral 0 to infinity 1 upon x square log of 1 plus x square into, rather, minus 0 dx. So we end up with integral 0 to infinity log of 1 plus x square into 1 upon x square dx, to be integrated by parts, taking this as function 1 and function 2. The formula for integration by parts can be written as integral function 1 into function 2 dx. In words, it is retain first into integrate second minus integral of differentiate the first function into integrate the second function, and this particular product is to be again integrated. This will be the formula for integration by parts. And of course, to choose function 1, we have a standard rule as LIATE, that is, choose the logarithmic, if not inverse, otherwise arithmetic, then trigonometric, and then exponential. Here we have logarithmic, so we continue with that, and it will be log of 1 plus x square, retain first, integration of second, e raised to minus 2 will be integrated as e raised to minus 1 upon minus 1. So retain first, integrate second. This will be between limits 0 to infinity. Minus integral 0 to infinity. Differentiate first. Log ka derivative will be 1 upon 1 plus x square into 2x, of course, and integration of 1 upon x square will be again x raised to minus 1 upon minus 1 dx. Now it's time to substitute the limits into it. Let us rewrite it for the time being as minus 1 upon x log of 1 plus x square, which is within the limits 0 to infinity, minus minus plus the second integral will be integral 0 to infinity 1 upon 1 plus x square, 2 I can take outside, x, and that x raised to minus 1 is 1 upon x dx. So this x cancels here. As we substitute the limit, at upper limit 1 upon x will be 1 upon infinity, so upper limit value will be 0. At lower limit 1 upon 0 is infinity, but log of 1 plus 0 will be log 1. Log 1 is 0, so upper and lower limit values of this particular integral will be straight away 0. And the second integral that we have is plus twice integral 0 to infinity dx upon 1 plus x square. This is the direct formula. It will be twice tan inverse of x within limits 0 to infinity, which will be 2 into bracket tan inverse pi by 2, sorry, tan inverse infinity minus tan inverse 0. So it will be pi by 2 minus 0. Answer is pi. So second one could be integrated without changing the order of integration. Answer is pi. Let us now solve the third one. In the third case, in the third problem, it is integral 0 to 1, integral 1 to infinity e raised to minus y, y raised to x, log of y dy. We are supposed to integrate with respect to y first, and there are three terms, as I have already said, to be integrated, and this integration could be a tough task. So first of all, we decide to change the order of integration. Change the order of integration, which is going to be a simple job for this third problem, because all the four limits are constant. We will simply switch over the limits. It will be integral 1 to infinity dy, integral 0 to 1 e raised to minus y into y raised to x into log y, to be integrated with respect to x. Now when we are saying that it is to be integrated with respect to x, except for x terms, all others can be removed outside that particular integral. So it will be e raised to minus y into log y into dy, integral 0 to 1 y raised to x dx. As we are integrating with respect to x, it is the formula like where y is constant, it is a raised to x, which has got integration as a raised to x upon log a. So it will be e raised to minus y into log y into, this integral is y raised to x upon log y between limits 0 to 1 dx. When you substitute, oh sorry, it's not dx, dy. When you substitute the values of x in this particular integral, we will write it as 1 to infinity e raised to minus y log y. At upper limit it will be y raised to 1 upon log y, minus at lower limit it will be y raised to 0 upon log y dy. Obviously this log y cancels and you will get the answer over here as e raised to minus y into y minus 1 dy. So we have got two integrals over here, or we can go for integration by parts. Instead of separating the two integrals, probably taking y minus 1 as function 1, arithmetic, because it is LIA. So arithmetic first and then it will be exponential. So y minus 1 as function 1 and e raised to minus y as function 2. We can go for integration by parts, and the value will come out to be retained first, that is y minus 1. Integration of e raised to minus y is e raised to minus y upon minus 1. This will be within limits 1 to infinity minus integral 1 to infinity y minus 1 is to be differentiated, it is 1. E raised to minus y to be integrated is e raised to minus y upon minus 1 dy. As we take minus sign outside and substitute the limits, y minus 1 में infinity substitute किया तो it is infinity minus 1, that is infinity, but e raised to minus infinity is 0, so upper limit value is 0. And at lower limit y minus 1 you are substituting y equal to 1, so 1 minus 1 will be 0. So the first value at upper limit and lower limit is 0, and the second integral will be minus minus plus integral 1 to infinity e raised to minus y dy. So we get it as, after integration, e raised to minus y upon minus 1 within limits 1 to infinity, it will be minus of e raised to minus infinity minus e raised to minus 1, and as we substitute it will be minus into bracket 0 minus 1 upon e, minus minus plus, answer comes out to be 1 upon e. Answer for the third problem is 1 upon e. Let us have a look at problem number 4. Limits are in terms of x. So these are values of y, and we are required to integrate with respect to y first. We can integrate this particular function xy with respect to y, probably without going for changing the order of integration. The problem can be solved. It is x equal to 0 to a, y equal to x square upon a, to y equal to 2a minus x, it is xy dx dy. Integrated as it is, we have x equal to 0 to a, x as it is, integration of y is y square by 2 between limits x square by a to 2a minus x dx. Half can be taken outside, integral x equal to 0 to a, x into bracket 2a minus x bracket square minus x raised to 4 upon a square dx. Further simplification is not possible, and x into 2a minus x bracket square also cannot be put in any simplified form. Only option that is left with us is to expand this and multiply by x, resulting in x raised to 0, x equal to 0 to a, it will be x into bracket 4a square minus 4ax plus x square minus x raised to 4 upon a square dx. When you multiply by x, it will be half integral x equal to 0 to a 4a square x minus 4a x square plus x cube minus x raised to 5 upon a square dx integrated as 1/2. 4a square is constant, integration of x is x square by 2 minus 4a integration of x square is x cube by 3 plus integration of x cube is x raised to 4 upon 4 minus 1 upon a square as it is, integration of x raised to 5 is x raised to 6 upon 6 between limits 0 to a. And so this will come out to be 1/2 into bracket 4a square into a square by 2, value at upper limit x equal to a, minus 4a into a cube by 3, value at upper limit of x is x equal to a, plus again x equal to a, it will be a raised to 4 upon 4 and minus it will be 1 upon a square into a raised to 6 upon 6. These are the values at upper limit, and at lower limit you are going to substitute x equal to 0 and all the terms contain x directly, so all the terms will have value 0. So lower limit value for this particular integral is straight away 0. At upper limit you will find that every term over here contains a raised to 4, a raised to 4, a raised to 4, and this is a raised to 6 upon a square, that is again a raised to 4. So a raised to 4 can be uniformly taken common. What remains inside is first term as 2, second term is minus 4 by 3, third term is 1 upon 4, whereas last term is minus 1 upon 6. LCM in this case comes out to be 12 and the problem can be easily solved. It will be a raised to 4 by 2 something upon 12. Here you will have to multiply by 12, it is 24. Then this will be 4 into 4 minus 16. This will be plus 3 and this is minus 2. And so 24 minus 16 is 8 plus 3 11 minus 2 is 9. So it will be 9 a raised to 4 upon 24. Of course you can divide by 3 and the final answer could be 3a raised to 4 upon 8. So answer for the fourth problem is 3a raised to 4 by 8. Finally, problem number 5. Again, limits are in x. So these are values of y. Problem number 5. Limits are in x. These are values of y. So on strip y varies from y equal to x upon a to y equal to under root of x upon a, and such strips are taken from x equal to 0 to a. So the given integral is x equal to 0 to a, integral y equal to x upon a to y equal to under root of x upon a, x square plus y square excuse me, dx dy. We are required to integrate with respect to y first and it is integrable. So let us proceed with the integration. X equal to 0 to a, x square y plus y cube by 3 within limits x upon a to root of x upon a dx. So it is integral x equal to 0 to a, x square at upper limit it is x upon a bracket raised to half. Better to write it in this form. Plus the second term it will be x upon a bracket raised to 3 by 2 with 1/3 which is already outside. Minus at lower limit it will be x square into x upon a plus 1/3 into x upon a bracket cube dx. This can be simply written as x equal to 0 to a. First term will be x square into x raised to half, so x raised to 5 by 2 upon a raised to half. Second term can be written as plus x raised to 3 by 2 upon 3 a raised to 3 by 2. This is minus only. X cube upon a will be the third term, and minus 1 by 3, it will be x cube upon a cube is the last term, to be integrated with respect to x. As we integrate it, it is 1 upon a raised to half, which is constant. X raised to 5 by 2 is integrated as x raised to 7 by 2 upon 7 by 2, plus 1 upon 3 a raised to 3 by 2. X raised to 3 by 2 is integrated as x raised to 5 by 2 upon 5 by 2, minus 1 upon a. X cube is integrated as x raised to 4 upon 4, minus 1 upon 3a cube. X cube is integrated as x raised to 4 upon 4. This is between the limits 0 to a. At upper limit, this is 1 upon 7 by 2 can be written as 2 by 7, and when I substitute x equal to a, it will be a raised to 7 by 2 upon a raised to half. So it will be a raised to 7 by 2 minus half, a raised to 6 by 2, that is a cube. In the second case, 1 upon 5 by 2, that is 2 by 5, and original 3 is there, so it is 2 by 15. It will be a raised to 5 by 2 upon a raised to 3 by 2, that is simply a, minus 1 by 4. It will be a raised to 4 upon a, that is a cube, and in the last case it is minus 1 by 12, a raised to 4 upon a cube, that is a. So these are the values at upper limit. Minus at lower limit, all the values are straight away 0. And so you find that there are two terms of a cube. So it is a cube into bracket 2 by 7 minus 1 by 4, and there are two terms of a having coefficients as 2 by 15 and minus 1 by 12. So here we can take LCM and write the answer as this is 8 minus 7 a cube upon 28, and plus it will come out to be 24 minus 15 upon 15 into 12 a. So this will be a cube by 28. This will be plus 9 upon 15 into 12. Of course this is 3 4s and 3 5, 1 by 20 a. Answer can be finally written as a cube by 28 plus a by 20. All the problems which we have considered up till now, they were considering the strips either parallel to x-axis or parallel to y-axis. But there are some problems which can be easily solved by what are known as the radial strips. We know that in the Cartesian coordinate system, when we have x-axis and y-axis, every point will be specified by two coordinates x and y. Say x for that point P and y for point P. The another system which is called as a polar coordinate system, this is Cartesian. In polar coordinate system, the same point will be represented as the distance of point from the origin called as r, and the angle subtended by the radial vector which is theta. The point will be specified as r comma theta. If the same point P is to be represented as r comma theta, then we get the formula for r as under root of xp square plus yp square, and as we know that this is distance yp and this is distance xp, this being a right angle triangle, and if this angle is theta, we can say that tan of theta will be yp upon xp, or we can write it as xp is equal to r cos theta and yp is equal to r sin theta. So changing from Cartesian coordinate system to polar coordinate system will be with the substitution as x is equal to r cos theta and y is equal to r sin theta. Again, there are two variables r and theta, and when we talk of radial strip, we will have to specify the point which is going to move along the boundary in terms of r, that is under root of x square plus y square, as well as the change of angle theta, which will be changing with time or whatever is the variable. So any curve, say x square plus y square equal to a square, can be transferred to the polar form with the substitution that r cos theta bracket square plus r sin theta bracket square equal to a square, which will be r square into bracket cos square theta plus sin square theta equal to a square. Sin square plus cos square is 1, so r square equal to a square or r equal to a. That means theta is not indicated, theta will be taking all possible values, and theta can take a value from 0 degrees when it coincides with original x-axis to maximum of 360 degrees. When we consider the polar substitution, the elementary area that we were talking of in Cartesian coordinate system, which was of the dimensions dx dy, and that particular elementary area in the polar coordinate system will be shown in this manner, because the radial strip when we take, it will be a strip which will be moving from the pole. It will not be called as origin, it is pole, and this is actually the initial line which is representing x-axis. This is theta. Angle subtended by this particular radial strip will be d theta, and we are talking about some distance, change in the distance. If this length is r, then we will talk of change in r, which is dr, and this will be the elementary area. Of course, using the Jacobian part, it is possible that we can easily prove dx dy is equivalent to r dr d theta. So in the integration, when we come across dx dy term, it should be substituted as r dr d theta. If you want, this can be easily proved, because it can be written as deba xy upon deba r theta, which is nothing but a determinant deba x by deba r, deba x by deba theta, deba y by deba r, and deba y by deba theta. Deba x by deba r, when x is written as r cos theta, it will be simply cos theta. Deba x by deba theta, r is constant, you are differentiating cos theta with respect to theta, it will be minus sin theta, so it will be minus r sin theta. Delta y by delta r will be simply sin theta, and delta y by delta theta, y is r sin theta, r is constant, derivation of sin theta is cos theta, and so this will be r cos square theta minus plus r sin square theta, so it will be simply r, and this can be equivalent to dx dy upon dr d theta, and you will find that dx dy is r dr d theta. So the problem in the Cartesian coordinate system, any problem of double integration which is in the Cartesian coordinate system can be very well converted to the polar coordinate system with the said substitution, that is x equal to r cos theta, x equal to r sin y equal to r sin theta, and dx dy will be r dr d theta. Even the boundaries are to be converted to the polar form, and by taking radial strips we can solve the problem. For example, if we are required to integrate some function, say double integral f of x comma y dx dy to be integrated over area A bounded by y equal to 0, that is x-axis, y equal to x, that is a line making 45 degrees, and x square plus y square equal to a square, then the region of integration will be actually 1/8 of the circle, because this is going to be the line y equal to x, this is x-axis y equal to 0 and circle, so the region bounded by these three will be this sector. Now this particular area can be converted to the polar strip, and then we can represent the circle x square plus y square equal to a square in the polar form as r equal to a. So on this strip r will vary from 0 to r equal to a, and then such strips, the lowermost strip will be over here at theta equal to 0, and the last strip, radial strip, will be over here, that is at theta equal to 45 degrees, that is pi by 4. And so the given integral can now be written as r equal to 0 to r equal to a. On radial strip it will be always variation of r first, and theta varies from theta equal to 0 to theta equal to 45, that is pi by 4. Function f of x comma y will change to some other function g of r theta, and dx dy will be written as r dr d theta, which is to be solved further. So the problem can be converted to the polar coordinate system, and at times it will prove to be easier, because you can imagine that if the strips would have been parallel to x-axis or parallel to y-axis, then there will be complicated things which will be coming into picture. That is one part. And secondly, sometimes the function also will be telling us as we should be integrating with respect to the polar form. For example, in one of our earlier problems we had something like log of x square plus y square to be integrated on some region of the circle. Now if this is converted to polar form, it will take a form as log of r square into r dr d theta. Not only that, this particular 2 can be coming outside, it will be 2 log r into r dr d theta. Of course this is integrable with respect to r, whereas if it would have been simply log of x square plus y square, then we have no means by which the integration can be carried forward, because we cannot adjust any variable like y or x to adjust the differential term of it and proceed further, neither that we have any formula for integrating log of fx. So these are the cases where we are required to shift to the polar coordinate system, and the integration will be the simpler case. There are some problems where the given curve, that is boundary itself, is given in the polar form, like one of the boundary of that particular bounded area, region of integration, is cardioid, that is r equal to a into bracket 1 plus cos theta, and it will be very difficult to get the corresponding Cartesian form of that particular curve. So if we don't have the Cartesian form, and though the function which is given to us is something like xy dx dy, still as the boundary is given in the polar form, we will be forced to switch over to the polar coordinate system by substituting x equal to r cos theta, y equal to r sin theta, and subsequently dx dy as r dr d theta, and the boundary is in terms of r and theta. Taking the radial strip, we can solve the problem. So in the next lecture, we will be going thoroughly through these radial strips.